B part 1, we're asked to figure out the rate of oxygen formation at a particular temperature using this graph which is on the next page. Now remember that K, the rate constant, varies with the temperature, so we can't just use the value of K that we got earlier on, because that probably doesn't relate to the particular temperature we're interested in. That's why we have to use the graph, and so it's simply a matter of working out, if the temperature is 550 K, what does 1 over T equal? And then we can read off what the natural log of K is, and hence we can figure out what K is. Okay, so we need to first of all remember that T here represents the absolute temperature in Kelvin. So we've got to remember that the temperature in Kelvin is degrees C plus 273. Okay, you have to learn that, and you need that in other things as well, like ideal gas law, for example. So that's something you need to have learned. And so 550 degrees C plus 273 is equal to 823 Kelvin. That's the first step. But we want 1 over the temperature, so we get 1 over T is 1 over 823, which comes to 0.001215 Kelvin. Kelvin to the minus 1 it'll be now, because it's 1 over T. Okay, so what we've got to do is, at that temperature, we can read off what the natural log of K is. So we get our ruler, and we say, right, if it's 0.001215, there's our, we're going to say we want the value there, so we can say, right, there's the line that we want, and we just read across to see what K would equal, or rather the natural log of K would equal when 1 over T was equal to that. And what you should get, which doesn't look quite right on here because obviously this is just sketched, but what you get off the actual graph is that log of K is equal to 1.25 at this temperature. So now we've got to change it from the log of K into the actual value of K. And if you look on your calculator, you can see what the inverse operation of the natural log is. Obviously, if you do maths, you know this, but if you don't, just trust your calculator, and it tells you that the inverse of the natural log is e to the x. So we get that K is equal to the inverse of the natural log of 1.25, which mathematically is equal to e to the power 1.25. So you can do it on your calculator, whichever way you want to think about it. It amounts to the same thing, and that comes out at 3.49. And remember, it's a first order rate constant, so the units are seconds to the minus 1. So then we can plug that number into this equation, and we get that the rate of H2O2 loss, because that was what was being measured in the experiment, is equal to K times the hydrogen peroxide concentration, which is 3.49, and it tells you in the question that the hydrogen peroxide concentration is 2 times 10 to the minus 3 moles per dm cubed, so it's 3.49 times 2 times 10 to the minus 3, which is 6.98 times 10 to the minus 3 moles per dm cubed per second. And if you're not careful, you might stop at that point and think, great job done, but there is a twist in the tail here, because the reaction, remember, is 2H2O2 goes to 2H2O plus 1O2. So the rate of formation of oxygen will only be half as great as the rate of loss of H2O2, because every time 2 of those are lost, only 1 of these are formed. So the final thing is to get that the rate of forming O2 will just be a half of this number. So it's a half times 6.98 times 10 to the minus 3, which is 3.49 times 10 to the minus 3 moles per dm cubed per second. And that's your final answer. Now you may not get exactly that number because it depends on the value you read off here, so you may have got a slight discrepancy in the value you read off in that graph, but it should be very close to that number, and that's the rate. So you have to be very careful here, because when you see natural log of k against 1 over t, your brain is going to think this is an Arrhenius question, but it's not yet. It's not asking about activation energies, so you don't need the Arrhenius equation at this point. This was simply about using the graph to read off in effect the value of k at a given temperature, and that's what led us to the rate. Part 2 is where it starts talking about activation energy, so this is where the Arrhenius equation comes in. So remember, the Arrhenius equation is given to you on the datasheet, and it's written in two forms. The first one is this, which is sometimes useful if you've got to plug two of the numbers in to find the third one or something like that. But that's not really the form to use when you have a graph like this. If you have a natural log of k versus 1 over t graph, then the form to use is the logarithmic form, which is also on your data sheet, which looks like this, and it says log of k is equal to minus Ea over RT plus log A. So that's as it's written on the data sheet. Now the thing to do is to recognise that if you just rewrite that ever so slightly, it becomes clear that it's the equation for a straight line, which of course is what you've got on the graph. So to do that, you just write it like this. Log of k is minus Ea over R times 1 over t plus natural log of A. Now if you write it like that, and you can see that's the same thing, because you get minus Ea times 1 on the top is Ea minus Ea, and then RT on the bottom is RT. So it's just the same equation. But the point about writing it like that is that you can now see explicitly that this is a equation of the form y equals mx plus c, which, as you know, is the general equation for a straight line. So y is the vertical axis, which is natural log of k. X is the horizontal axis, which is 1 over t. But it's these other two parameters which we're going to be concerned with. So m is equal to minus Ea over r, and remember that is the gradient. Okay, so you know that from GCSE maths, that if you have an equation y equals mx plus c, m is the gradient of the line. So if we can find the gradient of that line, that will be equal to minus Ea over r, and since r is just the gas constant that comes off your data sheet, you can use that to find the activation energy. C is the constant that's added on, and that, you can see, is equal to the natural log of A, the pre-exponential factor, and so that you can also find either from an intercept or by substituting back into the equation. But for this question, we were only interested in this one. So what you need to do then first is to measure the gradient of this graph. It's a slightly awkward one, just because of where the line is relative to the axes. The thing to do is, first of all, to register that you don't want to do it with a tiny little triangle. So don't do something like that. Just put a little tiny triangle on there and say, right, it's vertical divided by horizontal, because the error you introduce by using a very small triangle like that is massive. And so you're going to get very approximate numbers by doing that. So you want to make, pretty much as big a triangle as you can manage. So there are various ways you could do that, but I think what I would probably do is to say, right, well, let's take this line, which is 0.0011, and this line at the end, which is 0.0015, and say, right, that's my horizontal change, and then just register where the corresponding vertical values are. So for this point, just draw a line across here, and if you do that accurately on the graph, that comes to minus 0.38 on the actual graph that you had printed. And this value here, where it cuts that line there, comes out at plus 1.92. Okay, so now we've got a nice big triangle which is going to give us a nice accurate gradient. So remember that general definition for the gradient is that it's delta y divided by delta x. So as the horizontal changes from 0.0011 to 0.0015, the change in the x-axis is 0.0015 minus 0.0011. The corresponding change in the horizontal axis, well, when it was 0.0015, you can see it was minus 0.38, so it's minus 0.38 minus, and then when it was this value, you can see the y was plus 1.92, so it's minus 1.92, and if you crunch those numbers, that comes to minus 5750, and the units are Kelvin. It's easy to get the sign wrong at that point if you just subtracted these the other way round, just because that seemed more logical. For some reason you'd get plus 5750. But the point is, you can tell it's a negative gradient because the line is pointing downwards. So, you know, if you prefer, just think of how big is that distance compared to that one, and then just put the sign on by saying it goes downhill, but make sure you get the sign right. So it's minus 5750, and that's equal to minus EA over R. So you can see that if you multiply by minus R, the R's will cancel and the minuses will cancel, and you'll get the activation energy. So you get that EA is equal to the gradient times minus R, which is minus 5750 times minus 8.314. R, remember, comes off your data sheet, but you just want minus R, and that works out as plus 47,800 is the number. The units of that will be joules per mole, so you've got to be careful there, because obviously energies normally come in kilojoules per mole, but because R, if you look in your data sheet, is in units of joules per Kelvin per mole, when you crunch the numbers here, this comes out in joules per mole. So to put it in the more normal kilojoules per mole, which is what it asked for, that would be plus 47.8, so we're just dividing by 1,000 to put it in kilojoules per mole. And then it asks for it for two significant figures, which is therefore plus 48 kilojoules per mole is the answer. Notice I put the explicit plus sign in. You should always do that with energies in chemistry, whether it's just enthalpy calculations or activation energies in this case. If it's a positive number, you put the positive in front of it, and you may possibly get penalised if you don't. Okay, so that's how to get activation energy from one of these kind of graphs. Okay, so over the page now we're looking at catalysis. So now we're talking about an aqueous solution. If you read the question, aqueous solution of hydrogen peroxide, and the acceleration by addition of solid manganese 4 oxide. So first of all, homogeneous, heterogeneous, remember that's about whether the phase of the catalyst is the same or different from the phase of the reactant, and in this case they're different because you've got aqueous hydrogen peroxide, you've got solid manganese 4 oxide. So you need to spell out what's in different phases. People often lose marks because they say things like it's heterogeneous because it's in a different phase, and they'll just say, well, what's in a different phase from what? I don't understand what you're saying. So be precise and just say it's heterogeneous because the manganese 4 oxide catalyst is in a different phase from the hydrogen peroxide. Okay, the second part now is asking for an enthalpy profile diagram, and they've given you the axes. So we've got the reaction progress along the bottom and enthalpy up the side. And it's asking you to use that to illustrate how a catalyst works. So again, they've put this bit on for you, so you've got the aqueous hydrogen peroxide there, and it's an exothermic reaction, and so the products, which are water plus oxygen gas, are down there, and that is the enthalpy change of reaction. So now, the rate is controlled not by the overall enthalpy change, but by the activation energy, and that's what you need to mark on. So, in the absence of a catalyst, first of all, the idea is that there will be some kind of pathway like that that leads from the reactant to the product, and the activation energy is the height of the barrier that you need to get over. So the important thing is you've got to put that arrow on there, because the activation energy is not what the energy is at the top, it's that difference between where you start and where you end up. So you need to put that arrow on there and label that as the activation energy, and that's without the catalyst. Okay, so it's the amount of extra energy that the reactant molecules need to get, so starting from there to reach the high energy point on the curve. Now, what a catalyst does is to introduce an alternative reaction pathway with a lower activation energy. So that's what you need to mark on there. So again, there'll be some sort of curve which you can put on like that. And the point is that the high point on the curve now is much lower, and so the height of the arrow corresponding to the amount of extra energy you need to reach the high point is much smaller. So again, it's that arrow which is the activation energy. Okay, you won't probably get marks just for writing the profiles on there, just for drawing the curves. It's putting those arrows on there, and they should be one-way arrows, because it's the amount of energy going from the reactant to the transition state, the state at the top of the curve. So one-way arrows like that, and that's the activation energy with the catalyst. Okay, so you want some kind of diagram like that. And we come to the Boltzmann distribution question, and it's asking us again to explain how a catalyst works, but this time in terms of the distribution. So first, you've got to remember what this is and label the axes accordingly. So it's an energy distribution. So energy goes along the bottom, and the idea is that it's showing us what the likelihood is that molecules will have different energies. So what goes up the side is the number of molecules. Okay, so it's the number of molecules that have any particular energy. And the shape of the distribution, key feature is first it starts at the origin, so it must start there, rise up to a peak, and then come down a bit more gradually on that side, and tend down towards this axis. So it looks like it's going to, meet it when we get to some infinitely long distance up there, but never actually crashing into it, so that we want something that looks sort of like that. And then the activation energy, which is what controls, remember, whether a collision will be successful or not, will just correspond to one value of this energy. So we just mark a vertical line on here and say, right, this line is the energy which corresponds to the activation energy. And the area under the curve to the right of that line, so this shaded area represents the proportion of molecules which have enough energy to react when they collide. Now what the catalyst does, as we saw in the other diagram, is to reduce the activation energy to provide a new pathway with a lower activation energy. So this is the activation energy with the catalyst. And you can see that because it shifted to a lower value, the corresponding area under the curve representing the population of molecules with enough energy to react when they collide is that much bigger. And that's the point. So those are the features you need on the diagram, but in this case it needs a sentence or two to explain what's going on. So you need to say that because the catalyst provides a pathway with a lower activation energy, the proportion of molecules with enough energy to react when they collide will be greater. That's what the curve is showing you. So the proportion of molecules with enough energy to react when they collide is increased. But that's not enough really, because they'll still say yes, so why does that increase the rate of reaction? So you really have to spell it out. So you say, so successful collisions occur more frequently or more often. And that's the key idea, that because successful collisions occur more often, the reaction rate increases. Okay, so make sure you've explained it fully, because I think in that case the diagram's not enough, because they would say, well, what's that showing me? So that spells it out.